How do prime numbers reveal unique mathematical patterns? Imagine a world where some numbers seem to stand apart from the rest, like special keys on a piano that only play one note. These are prime numbers, and they hold secrets that can unlock fascinating patterns in mathematics. Prime numbers are numbers greater than one that can only be divided evenly by one and themselves. They are the building blocks of all natural numbers, as every number larger than one can be written as a unique product of primes. This idea is called the fundamental theorem of arithmetic, and it shows how essential primes are in understanding numbers. When you look at the number line, prime numbers appear scattered, but they follow certain rules. For example, all prime numbers greater than 3 are close to multiples of 6. They often take the from 6 times a number plus or minus 1. This pattern exists because numbers divisible by 2 or 3 are not primes, so primes tend to cluster around these positions. It's like they hide just outside the multiples of 2 and 3, making it easier to spot potential primes. Prime numbers also show interesting gaps between each other, called prime gaps. Sometimes, the gap between two primes is just 2, like 11 and 13, called twin primes. These pairs are special because they are very close together, yet whether there are infinitely many twin primes is still a mystery in mathematics. The way primes space can vary a lot, but researchers have found hints that there might be limits to how far apart they can get as numbers grow larger. Another intriguing pattern involves the last digit of prime numbers. When looking at large sets of primes, sumless digits are less likely to follow themselves. For example, primes ending in 5 are rare because any number ending in 5 that is larger than 5 is divisible by 5. This bias in last digits suggests that primes are not just randomly scattered but follow subtle rules, which mathematicians try to understand through complex conjectures like the K-tuple conjecture. Prime numbers are also connected to important mathematical functions. For example, the Euler product formula links primes to the Riemann Zeta function, which helps predict how primes are distributed among all numbers. This connection is vital for understanding the density of primes and their patterns. When performing basic arithmetic, recognizing these patterns can help you identify prime numbers more quickly. Knowing that primes tend to be near 6 times a number plus or minus 1 can narrow down your options when testing if a number is prime. Prime numbers are more than just special numbers. They reveal a hidden order in what seems like chaos. Their distribution, the gaps between them, their last digits, and their connection to advanced functions all show how primes follow unique mathematical patterns. These patterns help us understand the structure of numbers and give us practical tools for working with them in everyday math tasks.